Section 3.6, derivatives of inverse trig functions. So in this section, we're going to look at the derivatives of inverse trig functions. And before we do that, I want to review a little bit about inverse functions in general and the inverse trig functions in particular. So first of all, let me remind you how to find the inverse function. So suppose we're given f of x equals 3x minus 2, and we want to find the inverse function of that. We first substitute y in place of f of x. Then I swap the position of the x and y. And then I solve for y. So here I'll add 2 and divide by 3. So that's x plus 2 divided by 3 equals y. And this is what I call the inverse function once I've solved for y. And I denote that with an f inverse of x, f raised to the negative 1 power. This, by the way, I could simplify as x over 3 plus 2/3 by breaking it into two fractions. And this would give me a line. And the next question is sort of graphing the two functions, see how they're related. So y equals 3x minus 2, that crosses at negative 2, and it has a rise. The slope is 3, so if we run 1, we rise 3. Run 1, we rise 3. Go down 3, we go over 1. That green line right there is my f of x. And then how do I graph f inverse? If I wanted to just do it from the graph, I would first put in the dotted line where x equals y, and then the graph of f inverse would just be flipping this green line over that blue line. So here this is crossing at 2 there, it'll be crossing at 2 here, and here that's 1 away diagonally, so it's going to be 1 away diagonally there. And then I draw that line in. That's my f inverse of x. And you can check that this actually makes sense. Here's my f inverse function, and it's crossing at 2/3 right there, and it has a slope of 1/3, so it's positive. If I run 3, I go up 1, run 3, go up 1. So that does make sense. And then the last thing it says is use algebra to show they are actually inverses. So how do I do that? What I'm talking about here is the fact that if you substitute in an inverse function in for x for the regular function, that is, if you compose a function and its inverse, it should always give you x. So if I do that here, my f of x is 3x minus 2. So if I do 3, in place of x, I'm now going to put x plus 2 over 3, because that's my inverse function. And then the minus 2, actually I should write it like this. F of f inverse of x is equal to 3 times x plus 2 over 3 minus 2. And I can cancel these 3's. Come back. And I'm left with just x. Come back. I'm left with just x plus 2 minus 2, which those of course cancel, so I just get x. So that's my confirmation algebraically that these are in fact inverse functions. And that's my confirmation graphically. And you can also do f inverse of f of x, and that should still give you x as well. Now the inverse trig functions are written as arcsine of x, arccosine of x, and arctangent of x. And we also write them as sine inverse of x. So in particular, these mean the same thing. If I write arccosine of x, that's the same thing as inverse cosine of x. I prefer the arccosine notation though, because this inverse notation is a little bit misleading, and let me explain why. We write cosine squared of x to mean cosine of x squared, but cos inverse of x is not the same thing as cosine of x raised to the negative 1. These are very different functions. This is the inverse function of cosine, and this, what's cosine of x to the negative 1? Well, that's the same thing as 1 over cosine of x. That's secant of x. And secant is not the same thing as inverse cosine. So that's why I often prefer the arc cosine notation over this one. And inverse trig functions do satisfy these properties, though, that if you take f of f inverse of x, or f inverse of f of x, you get back x, with a slight caveat. So let me say it this way. If you do cosine of arc cosine of x, that equals x, or tangent of inverse tangent of x, that equals x, or sine of inverse sine of x, that equals x. Guaranteed 100% of the time. But if you do it the other way, if you do arc cosine of cosine of x, that equals x, but only for x values in a certain range. That's only for x values between 0 and pi. And similarly, if you do inverse sine of sine of x, that equals x only for x values between negative pi over 2 and pi over 2, and the same thing, those same bounds work for tangent of x. And the reason is that when you try to flip this function to make the inverse graphically, when you look at that, you end up with something that's not a function, and you have to adjust the domain and range. So let me give you an example here. Let's just look at y equals cosine of x. Here's 1, here's negative 1. Let's say this is pi, 2 pi. It looks like this. Our normal cosine graph. And if I were to flip that, I would be drawing in my line at y equals x. And when I flip this over that red line, instead of going along the x-axis, this graph is now going to go along the y-axis. So it'll look like this. And now we have a problem because this isn't a function. It does not satisfy the vertical line test, because if I draw a vertical line, it's hitting in more than one place. So we went from a function, we tried to do the inverse, but all of a sudden we don't have a function defined anymore. And the reason is that cosine x is not 1 to 1. And you probably talked about that in pre-calculus. So what do? So this is not a function. So to fix it, what we do is we basically chop off the graph. Uh-oh, that was not supposed to happen. We chop off the graph at these two spots. We chop it off. I don't want that to happen. There and there. And when we quit doing that. When we do that, our graph just looks, we just get this piece of it. This is 1, this is negative 1, and that goes up to pi. And now if we cut this, just this piece off, now all of a sudden it is a function because we don't have the other parts to give us more than one value. And this is the graph of y equals inverse cosine of x. And what we actually did is we restricted the range of the function. So what is the domain? What is our domain and range for this? So the domain is just values between negative 1 and 1. Remember, domain is our possible x values. And the range is just between 0 and pi. And those are the values for arc cosine. If we wanted to write similar things for inverse sine, our domain would still be negative 1 to 1, but the range will now be negative pi over 2 to pi over 2. And for inverse tangent of x, which, by the way, we've talked about this graph before. It looks like this. It has a vertical asymptote at pi over 2, sorry, horizontal asymptote at pi over 2 and a horizontal asymptote at negative pi over 2. The domain of that one is all reals. and the range is negative pi over 2 to pi over 2. And the range here, these are the same values that I was getting up here for the places where the inverse function worked the other way. And in particular, how this often works out in calculation is consider the situation of y equals inverse sine of x. Well, what does it mean if y is equal to inverse sine of x? That means that if you do sine of y, you get back x, right? If I do the sine of both sides of this, the inverse sine would cancel out here, and I would get sine of y equals x. So for example, if I was looking for the inverse sine of square root of 2 over 2, and that was equal to y, I would have to ask myself, sine of what thing, sine of y, is equal to the square root of 2 over 2. And then I could look at the unit circle to figure out, oh, y has to equal pi over 4. And the trick here is that if I do sine of 3 pi over 4, that also gets me square root of 2 over 2. But 3 pi over 4 is not in the range of inverse sine. It's too big. It's bigger than pi over 2. So when I do the inverse sine of square root of 2 over 2, I only get this one answer of pi over 4.